It is part 2 of section 4.3. In the first part, we considered the trapezoid rule. In this part, we'll study Simpson's rule and Simpson's 3/8 rule. For given partition of the interval AB, the trapezoid rule uses locally linear interpolating polynomials, each of which is formulated on one subinterval. We may utilize locally quadratic interpolating polynomials formulated on each two subintervals. Furthermore, 3 and more subintervals can be combined for high-order interpolating polynomial. Simpson's rule uses two subintervals, and it results from integrating the second-order Lagrange polynomial with 3 equally spaced nodes, x0, x1, x2. x1 is the midpoint of x0 and x2. Here we have the definition. Approximating f by the quadratic interpolating polynomial on the interval x0 to x2, the elementary Simpson's rule is defined as in this equation. Here, this is the integral of the second-order interpolating polynomial in Lagrange form. We can rewrite in this way. Once these terms are evaluated, then we can get this formula. One contribution from x0, 4 from the midpoint, and another one from x2. So there are total 6 contributions and divided by 6. So this portion is a kind of average height, and 2h is the interval length. This is the elementary Simpson's rule. Here we consider graphical interpretation. We use f of x cubed plus 2 sine 2 pi x, and with one partition from 0 to 1, and we'll try to get integral. So 0 will be x0, and 1 will be x2, and x1 must be 0.5 here, midpoint, so that we have here point and midpoint and right end point. So the function value for f, this is f, and function value will be here and here and here. Now the quadratic polynomial, interpolating polynomial, will be this one, so that the result from the integration must be this area of this shaded region. Now the output is 2.25, which is the exact value of the problem. It must be exact. The reason is, now for this portion, the error must be 0, because at 0 and 2 pi and midpoint pi, these values are 0, so that, and also integral of that one over 0 to 1 must be 0, so that no error from this one. And later in an error analysis, we'll see that Simpson's rule has error, and its leading error term is fourth derivative of the given function. If you make fourth derivative, then that is 0, so that there is no error. The output must be exact. The 2.25 is the exact value. Now we have the elementary Simpson's rule. Now we have to analyze error. The error for the elementary Simpson's rule can be analyzed from this equation. that is the error term from interpolation error theorem. We are using second order interpolating polynomial, so that your derivative is third and 3 factorial and 3 points product here. Once you can get the integral, then it must be your order h to the 4, because here now that is a kind of a third order and along with one order from the domain, so that it must be fourth order. However, by approximating the problem in another way, we can show that the error is in order 5. Let's do it. Error analysis for the elementary Simpson's rule. We'll use the Taylor series expansion. It follows from the Taylor's theorem that for each x in the interval, there is a number psi such that f of x can be written in this form. Now the expansion is about the midpoint. Now we integrated the terms in this equation over x0 and to x2. Then here we have these 4 terms, the antiderivative of these 4 terms. We can get it easily and must be evaluated in x2 and x0, and we have to get the difference. Now the integral of this error term, the last term, also should be computed, but it can be easily computed by using the weighted mean value theorem on integral. This portion is non-negative, so it's not changing sign, so that average value of this portion can go out, as in this term. And here, this portion can be computed easily, and this is the final result for the integral. Okay, for these 4 terms, here, once x is x2, then there is h squared. Once x is x0, then it's minus h. Minus h squared is also the same h squared. So that after evaluation, and this will be 0. And similarly, also, that must be 0. So we have this term and that one, and from error, so that is exactly these terms. And now we have to replace this term by something. And earlier, we know that f2 double prime at x1, this is a midpoint formula using x0, x1, x2, and the error is a second order. We know that. So we'll replace this term with that here. Then from this portion, we have that one. And from this portion, we have that. Now, this one, h squared, h cubed, so that this term is in order h to the 5. And we combine these 2 terms, and we simplify this addition. Then we can get this one. That is exactly the same as the Simpson's rule. So that the Simpson's rule has order 5 error. And earlier, we said that by using another technique, we can get the error in order 5. So that is exactly the Taylor series expansion technique. Okay, so locally, for each 2 subinterval, the elementary Simpson's rule will have order h to the 5. Now, this Simpson's rule can be applied for each two subinterval. Once the interval a to b is partitioned into even number of subintervals, then we can apply the elementary Simpson's rule on each two subintervals. Like here, okay, a to b, the integral of f can be written here now, n over 2 summations. Now each one is integral of f over two subintervals. So far, we don't have any approximation. Now, this integral can be approximated by the elementary Simpson's rule. So that is the formula for composite Simpson's rule, and it can be implemented. For each two subinterval, we are adding this 3 value and add again up to the last two subintervals, and then we scale by using this value. Then that's the program. Okay. Show that the error term for the composite Simpson's rule becomes that one. You can prove this one quite easily. Here, for each two subintervals, it has this error, and now we have to add this error and n over 2 times. Then you can get here this one. The way of getting the error is quite similar to the composite trapezoid rule, so that you can do it yourself. Okay, now we'll go to Simpson's 38th rule. And now when we are using 3 equal subintervals, the combined as a set, then we can get here Simpson's 38th rule. Now for x0 to x3, 3 subinterval, that is x0, but is equally spaced x2, x3. For this 3 subinterval, we can get here third order polynomial, interpolating polynomial, and now the integration of f can be here approximated by the integration of the third order interpolation polynomial. Now if you do the computation, then we can reach at that terms, and then the error term from interpolation error theorem can be integrated to get this value. So that is the elementary Simpson 38th rule. Now for this one, and here we can apply for each subinterval over the whole domain, then it becomes composite Simpson's 38th rule. And the error term also can be analyzed quite easily, and assuming n is the multiple of 3, and we apply the Simpson 30th rule, then the error will be added here n over 3 times, so that the error must be here sigma I is from 1 to n over 3 and minus 3h to the 5 over 80, and here f fourth derivative at some point psi I. Now the average value can go out, and here, okay, maybe minus 380 can also go out, so that is, okay, let's put 30 behind, but anyway, minus and f fourth derivative at some point divided by 80. 80 can go out, and remaining part is a sigma and 3h to the 5. Now, I is from 1 to n over 3, so that this portion becomes here 3 times, okay, 3h to the 5 times n over 3. So 3 can be cancelled. So that is same as h to the 5. N is the same as b minus a over h. So that we are using b minus a over h, which becomes h to the 4 times b minus a. So that here the final answer must be here now minus h to the 4, h to the 4 and b minus a over 80 and f fourth derivative at some point, right? So that's the final answer for the error for the Composite Simpson's 3H rule. Okay. Now, when the n is not even, then if it is n is even, then you may apply the Simpson's rule for each two subintervals, so that you can formulate the Composite Simpson's rule. But if n is not even, then you may approximate the integral by combining the Simpson's rule and Simpson's 38th rule. For example, n is 13, then you may apply the Simpson's rule for first 10 subintervals, so that there are 5 applications of Simpson's elementary Simpson's rule, and for the last 3 subintervals, you may try to apply the Simpson's 38th rule. In this way, you can enjoy high accuracy for the integral. Here we have a self-study problem for this one from 0 to 2. Now, here the true value is this one, and we'll try to use 6 equally spaced nodes, so that there are n is 5 subintervals to approximate the integral. And first we'll try to use trapezoid rule, and now secondly we may try to use combination of Simpson's rule and the Simpson's 3H rule. There are 5 subintervals, so that for the first 2 subintervals you can use the original Simpson's rule, and for the second 3 subintervals you can use Simpson's 3/8 rule. Then here for trapezoid rule we have that result. The error is this amount, and if we are using the combination of Simpson's rule and Simpson's 3/8 rule, then here this portion and that portion makes the quantities, and result is given in this way. For that combination of Simpson's rules, the error becomes this one. So you can use Simpson's rule for any number of subintervals, and try to use the original Simpson's rule more, and for the last possibly last odd 3 subintervals you can use Simpson's 3/8 rule. But if the number of intervals is even, then just use simply the Composite Simpson's rule. Then you can get really good accuracy. Okay, that's the end of the section. Thank you.